All right, so the first thing we're going to do is we're going to define some weights. So I've already downloaded these weights. I just went to Google and I searched pre-trained weights for the AllCNN network, and I found this individual on GitHub who had actually taken these and implemented the AllCNN in TensorFlow and Keras, and then trained them using modern GPUs, and actually have the weights available here on their GitHub page. So the one we want is the AllCNN weights file here. This is the HDF5. This is the AllCNN trained weights. So if you click on this, you can come down here and actually just download these. They're pretty big. I mean, this is 1.3 million parameters, so it takes up a couple megabytes, but that's okay. We're going to use this for our network. So again, if you just Google the AllCNN pre-trained weights, you can pull up this user, or Google this individual user. You can find the trained weights to the AllCNN network in this HDF5 file in this GitHub page and download them through that. So that's what I've gone ahead and done that already. And as you see, I've copied that file over here into the same folder as I'm running this Jupyter Notebook. So again, this just shows the directory here. So copy that weights file into that same directory, and then you'll have those available there. Okay, so and then we can go ahead and switch things around here. So instead of just building this model, I'm going to define the weights. So weights is going to be equal to the AllCNN weights underscore 0.9088 underscore 0.4994 .hdf5, which is the file type. This is the file type that Keras can accept. If you're using other deep learning libraries such as Caffe, you're going to have different formats for saving and loading the weights. For example, in Caffe, it's going to be a Caffe model file instead. All right, and now when we build this function, let's go ahead and pass it the weights. So we are now going to load in these weights, and this is going to work nicely because we actually defined this in our network above. We had if weights, and since we passed it, weights is going to have a value, so this is going to be a true, and then it's going to do a model.loadWeights, which is this weights file here that we defined. Okay. We just have to change a couple of things. We don't need our training parameters anymore. We're going to skip this training phase. And instead of fitting the model, we're actually going to test the model with pre-trained weights. All right. So instead of the model.fit, we're going to get rid of this. We're going to have a scores equals model.evaluate. Instead of fit, we have an evaluate here. And we're going to do this over our testing data set now. So xtest and ytest. And again, let's pass this a verbose equals 1 so it'll print out some information for us while it's evaluating them. Finally, at the end, let's go ahead and print accuracy. And this is simply going to be the scores 1. It's the second part of the index. So this will give us our accuracy there. Okay, so we should be good to go. We have these weights files that hopefully you downloaded along with me from the GitHub page. We've passed those weights to our AllCNN network, and we're now evaluating on the testing data set since these should already be trained up and ready to go. So let's go ahead and run this. This is going to print out a model summary for us as well, just like it did before. So again, we have those 1.3 million parameters. And here we go. So now we're into the evaluation phase. So you notice that instead of the 50,000 images here now, we only have 10,000 images, and we're moving through them pretty quickly with that batch size of 32 still. So this is going to go through this much more reasonable time. It's going to take approximately 4.5 minutes longer to get to the end of this. instead of 500 hours, that is something I can support and get behind. So I'm going to pause this video for the next 4 minutes, and when we get to the end of this, I'll come back. So hopefully yours is training along with me, or not training, or evaluating along with me, and then we can all come out on the other side and see how accurate this network is. All right, so I'm going to pause this, and I'll talk to you in a sec. All right, here we are, and we're coming down to the final seconds here, so we'll see the accuracy that this is able to produce in a second. As soon as this makes it to the end, it's been able to go through all 10,000 of those testing images in the validation data set. And here we go. An accuracy of 87.51%. So not quite state-of-the-art, but still pretty impressive, especially considering humans are only at 94% for this task. And this is probably just based off the way the individual from this GitHub page trained this network. I know that in the paper they go into a fairly extensive data augmentation process. Data augmentation means adding slight variations to the images, such as maybe rotations, maybe slight blurring, some noise, to help the network generalize further to the testing data set. So it is probably just the way that the individual trained this network that they weren't quite able to get as high of a percentage as they report in the paper. However, 87.51% is still very impressive, especially since we were able to just load those weights straight in. We didn't have to mess around with any of the training at all, and we were able to achieve these results by simply passing those weights and evaluating on the testing set. So that's pretty cool. However, the cool part of these networks is actually making the predictions and seeing those predictions. So let's go ahead and dive into that a little bit. We're going to define a dictionary of the class labels and names, and then we're going to use this network to print out a prediction for images that we pass it. So let's go ahead and start that. We're going to start by making a dictionary of class labels and names. So classes, we simply have the 0 to 9, so we can pass 0 to 10 here. The 10 is non-inclusive, so this is going to print out 0 through 9. And then the names, I'm pulling these straight from this page right here, where it defines them all. We're just going to make a list. So we have airplane, comma, automobile, comma, bird, cat, deer, dog, and then the last couple ones of here. We're going to have a frog, horse, ship, and then finally we have a truck. Okay, so those are our names. Let's go ahead and zip these together. So we're going to make a dictionary as well. And what we want is a dictionary of class labels. So class labels we can define, it's going to be a dictionary of zip, classes, and names. Okay, so there's that. If we do a shift enter here, that'll run. Let's actually print out this so we can see what we produced. Class labels. So 0, airplane, 1, automobile, 2, bird, etc., etc. This is a dictionary with the class label corresponding to the key, and then the value being the name of the particular class. Spell airplane correct there. So this is going to be handy because then we can change these class labels over to the names just so that we can more easily see whether or not our predictions are correct. All right, so let's generate a batch of 9 images to predict. So what I'm going to do is I'm going to say batch is equal to x test. I'm going to pull these from the test. You can do whatever images you want. I'm going to do 100 to 109. So that's just 9 images from the X testing data set. Labels is going to be actually the np.argmax ytest for these 100 through 109. axis equals -1. So a couple parameters we have passed there to get the labels, but that's okay. Let's go ahead and make these predictions. Predictions, and this is really easy with Keras, model.predict for this batch verbose equals 1, so that it'll print out some information for us. All right, so let's run this, see what we get. So it's making that batch, and really quick, 49 microseconds, it's able to predict all of those images, all 9 of those. So let's print out these predictions, see what we have. Print predictions. Okay, this is probably not what you were expecting to see. And actually, so these are class probabilities printed as floats for each particular image. So if we do a shape here, we see we have 9 images, a length 10 for each particular one. And so what this is, for example, if you look at this first image, this is going to be the probabilities for each particular class. So this is the softmax output. This makes sense if you understand the softmax, what it's doing. You're going to have really small probabilities for most of these, and then a very large probability for one particular class. So these are just float values, probabilities, outputted from the softmax layer. So we're going to have to process these a little bit if we want to get actual class labels. So these are class probabilities, and they should sum to 1, because there's a 100% chance that it's one of the classes. So let's just make sure that that's the case. Let's print the np.sum, and the image is going to be all of the particular float probabilities. So let's do this. And indeed, we see that they sum to a 1.0 exactly. So there's a 100% probability that it's one of the 10 classes. And so we can actually convert these to class labels using the np.argmax function here to convert class probabilities to class labels. So let's go ahead and do that, and we'll see how that works. So class result is going to be equal to np.argmax predictions. Axis, we're going to need a -1 here as well. Axis -1. So let's print out these class results. Awesome. So here we go. Now instead of the float class probabilities, we have actual class labels, that integer value for each one of these images. And now instead of a 9x10 shape for the predictions, we have this simply a length 9 vector with the class label for each particular image. Okay, so let's plot some of these out, and we'll compare them to the actual images. So, I mean, we want to do a visual check to make sure that we're actually making these correct predictions. So let's again create a grid of 3x3 images. We're going to do this a little bit differently than we did in the first time. We're going to do a figure, and axis is going to be equal to a plt.subplots. So we're going to define this ahead of time so that we can set this fig size a little bit differently. So there's that. And we also want a subplots adjust. We want an h space equals 1. So this is going to give us some room to add in the labels as a title. Axis, we want to do axis.flatten. All right, so that's just a little pre-processing of our PLT figure to start. Now we can actually dive into the for loop. We're going to do it and enumerate here for that batch of 9 images so that we can index. We can use indexing. So we're going to start by determine label for each prediction, and we're going to set the title. So to do that, we'll use another for loop for key value in class labels, which was the dictionary we defined above, dot items. So this is going to loop through the key and the value for each particular entry in that dictionary. And we'll say if class results of I is equal to the key, we'll set the title here. Prediction. And then we'll add in a new line character here. Actual. Do no space there. So we'll print out the prediction and the actual value. Dot format, substitute in some variables here. So class labels for the key. So this will give us the name. And then the class labels of I. So this is going to be the actual, and this is going to be our prediction. Okay, that should be good to go. But that's just a text string that we define as our title. We're going to set the title for this particular subplot using this set title command. We'll pass it that string that we just produced. And we're actually going to format these a little bit. We'll get x-axis, and what we're going to do is we're going to do a set visible equals false. These are images. We don't need axis here, axis tick marks and stuff like that. So we'll do this for both the x and the y-axis. Set visible false. There we go. Once again, we're simply looping through here, so we need to still plot this image. So we'll do an axis i.imshow. And remember, these images were shape 3 by 32 by 32. So again, here before we plot this, for the sake of PLT, we're going to have to do a transpose, just like we did before. So flip this around so that those channels are listed after the height and the width of the image. And then finally, we'll come out here and we'll do a show the plots, which is simply a plt.show to display this figure. All right, so let's go ahead and do a shift enter here. This will think really quick. And here we go. So we have our 9 images, we have our prediction, we have our actual value, and for these 9 images, we were actually able to get all of these correct. So our neural network, the AllCNN with the pre-trained weights, is forming these predictions here for these images. So deer, dog, frog, etc. And it did really good for these 9 images. It even was able to get a frog here. That's pretty hard to see, as well as a ship here. So if you want, go ahead and play around with the batch of images that you produce. You know, instead of taking these images, maybe take some other ones. Find a set where it makes an incorrect prediction and see if you actually would have gotten the image correct yourself. So this is pretty cool, though. We're able to actually predict the particular class, what is in these images, object recognition, a standard task in computer vision using the AllCNN network, which we built and defined in Keras, and then loaded pre-trained weights so that we were able to deploy it towards this data set. So really cool results. You might be thinking, though, so how do I use this in, my job, my company? We don't necessarily care about predicting cats. We want to do something different than that, but we still want to do object recognition. For that task, you would essentially take something like this. You would take these pre-trained weights, but then you would do fine-tuning. So additional training on your individual data set to convert some of these CNNs into a network that can produce results for your data set. So fine-tuning as well, you're going to want a GPU for that. You don't want to do fine-tuning on a CPU because, again, this is going to have to do many epochs, a lot of training iterations. So you want it to be pretty quick. However, we can use a lot of the information that has already been learned by this network. So in the pre-trained weights, you have like feature extractors. In some of those first layers, you have different groups of neurons that are potentially, detecting edges, detecting shapes, different features. And so those things transfer really well. So if you're using this on your own data set, all you have to do is fine-tuning. You don't have to do that initial training phase, training from random weights. So that'll save you a lot of time as well. But for this project, we're going to call this here. We looked at loading in the data set from Keras, the CIFAR10 data set, how we process that, how we convert the labels to categorical labels as one-hot vectors. We looked at loading pre-trained weights, building the all-CNN network in Keras based off the paper striving for simplicity, and then using that network to make predictions on some of these images. So I hope you learned a lot in this tutorial about object recognition, building models in Keras, and actually how to deploy them. So thank you very much for listening. I hope you enjoyed it. I know I had a good time producing this tutorial. So thank you very much.